Hello and welcome to the Code Maven channel on YouTube and our meeting. Thank you for everyone who is arrived to this meeting, and especially to Jacob, who is going to give the presentation. If you are unfamiliar with the channel, then we have these live presentations, meetings with live presentations, mostly about stuff related to Python and Rust programming, and also something about Git and version control and this area. My name is Gabor. I am the host of this. I teach Python and Rust at corporations, and I also help companies to get started with test automation and continuous integration area, that sort of area. And we have this meeting so people can share their knowledge with each other. So thank you for arriving. And before I let Jacob start talking about himself and introducing himself, please like the video, follow the channel. I always forget to say it, so now I remembered. So thank you, and it's yours.
Okay, we're going to try to make it as a conversation as much as possible. My name is Jacob Barhak. I've been developing disease models since 2006, so it's about 19 years now, a bit less than 19 years. And I have technology for disease modeling. Now, disease modeling means computational disease modeling, and I use a lot of Python. This is actually when I was introduced to Python in 2006, and all of this project was made in Python. It requires a lot of computing power, and the idea is to be able to explain diseases. So I started with diabetes. I was actually hired by a university as a programmer to actually write disease modeling software. I'm still using an offshoot of the same software like 19 years later. Now it's called MIST, the microsimulation tool, and it allows you to simulate many individuals going through a disease, and you define what the disease is. I started with diabetes. I actually got to the point that diabetes, I have one of the most sophisticated diabetes models worldwide, and this is patented technology. And at the end, you will see I have a conflict of interest statement because I believe this technology is worth a lot. So whatever I'm telling you, take it with a grain of salt. This is developed technology. Everything that I promise you, double check. The nice thing about this technology, it does the double checking for you for some degree. We'll explain it later. It uses some AI ideas and technologies to actually implement what's happening here. But it's not the AI that you're familiar with. It's a mix. And this is why it's patented. So let me explain what happens with this technology. I started with diabetes in 2020. COVID arrived to the US. I was in the US, and I started migrating my technology towards modeling COVID. And now I can explain COVID. But let me tell you what explain means. Oh, by the way, this presentation was given in many places. You can follow up how it changed, because it did change. All of those things you can download on the links. At the end, you will have a QR code. Actually, I'll show it to you now, but you will have a QR code that you can download this or actually view it. You'll need a strong machine to actually view it because it's a huge file. It's like a quarter of a gig size to actually download and view on your browser, but it has everything, including results, and it is interactive. It's an HTML file. I'm using Python technology called Holovis to actually do this. But it's less about Holovis, more about disease models. Later on, you can ask me about everything else. So you can download and see how things changed, even in my perspective. But now I believe things have been stable for the last approximately 2 years. So I'm pretty sure I can explain, at least in the US, what happened with COVID. And explain means, let's take it a step down before I show the model and explain it. Think about it. We might have more pandemics in the future. We probably will. We actually have them all the time. We have many diseases going on. But can we explain really what's happening? I was amazed when I started working with the medical people that how little they know about some of the things going on. And the fact is they are overwhelmed with data. The fact that they can remember and do something good is miraculous. And this speaks a lot about their profession. They are doing the best they can, but they cannot even memorize the medical papers coming out every 6 seconds. In every 6 seconds, a new medical paper coming out. There's no way one doctor will remember it all. And I'm not talking about all those medical databases, huge amounts of data that are being accumulated by bodies like the National Institutes of Health. All of this means that we need now to help computers help up crunch all this and give us good results and good explanations of what's going on. Because the way we are dealing with medicine now will change with the data. It's already changing. And this model and many other tools related to it will change it. So now let's go back to the model and explain how I can explain things. So the reference model for disease progression is kind of a statistical model. What it does, it says each disease has states. It's a state transition model where you can be either no COVID or can be COVID infected. You can recover or die from COVID. Notice that there is no error back from recovered to infected because I'm modeling the beginning of the disease, April 2020. Because the idea is that the next disease, we want to have a tool that will explain it to us in reasonable time. And I believe this is one of the tools that can help do that. So I'm trying to extract from the beginning data that people accumulated. I'm using the COVID tracking project data. They allow me to use it, even for commercial purposes. And you can actually go and track and see for each state in the US how many people got infected, how many people died, and they kept a pretty good record about it. And later on, there are other organizations that took over, but they were, I believe, the best at start. So I'm using that data, and now I'm trying to get a model that explains all those numbers that they appear, that they report. So to do this, I assume that there are those states, and this is the beginning of pandemics, so there is no reinfection. And I'm trying to match their numbers. How do I try to match them? Each error has several words above them. Each word means...
Wait a second, Jacob. Jim is writing that screen share not showing if that is wanted. I see on the screen these boxes of no COVID.
No COVID, COVID infected, possibly hospitalized. Jim, look if you have the option of actually choosing what screen you choose, because sometimes you can choose, you can see the shared screen. I can stop the share and share it again if it's okay with you guys. Or Jim, did you find the share?
I'll look, Jacob. Don't let me take you out of flow. Go, please proceed. Thank you.
So look at the link I sent you. You can actually bring up the presentation and follow up. I'm on the second tab called Introduction. It's an interactive, on your machine, you should be able to download it. You have good Wi-Fi, just download it to your machine and you can follow me there if you don't see the presentation.
Got it. So, it's loading.
Yeah, I know. It takes a minute to load. It's huge, but it has everything encapsulated. Part of the reason is to keep it reproducible as much as possible. At the end, you'll see a reproducibility section. I don't give away all the code, but I do keep track of everything that I noted. Like you see all of those boxes here. Those are all the references where you can actually extract the data. And some of the links actually became defunct. I found some other links so I can show you where I got the data from, or made sure that people can actually try to reconstruct this as much as possible, because we have a reproducibility crisis in science. Anyway, back to the boxes. So on top of those boxes, you'll see words like infectiousness, transmission, response, recovery, and mortality. Each one of those represents not one model, but many models. The technology that I'm using is called an ensemble model. An ensemble is like a choir in music. Well, ensemble models are very similar. You don't have one model, you have many of them. So I have many models for infectiousness, many models for transmission, many models for response, many models for recovery and mortality and hospitalization, you'll see later. But on top of it, I actually have an observer looking at all of this saying, your numbers are wrong. So you have to actually correct them because your observer actually, you have multiple observer models, each one seeing something different, telling you something different about those numbers. So you incorporate all of those, and now you have many, many, many models, and you have to run them all, and it takes quite a bit of computing power. Later on, I'll show you. I have a computer here who's still crunching data because I'm still working on this and making sure that my numbers are okay. So all of this takes a lot of computing power. You will see later on, this computation took about 3 years of computation on a single CPU. The ones I'm working on now will take half a year on a big 24-core machine, 32 threads. So, and when you run it on the cloud, it takes many, 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 many processors, because this takes a lot of computing power, just like AI, because it uses AI technology. We're going to talk about it later in a second. So I take all those models. I also take information from the COVID tracking project about what happened in each state, like numbers of, and you'll see some of those numbers later. I have information from US Census about each state. The states are not the same. They are different sizes, different population density, different age curves, population curves, it's called. Also, there was information about number of interactions and even the weather. I include the weather as part of the simulations, and later we'll ask some questions. But let's show you what the models look like and why they are the way they are. So let's explain one motivation why this is important to have a model like this. In the DHS is the Department of Homeland Security in the US. During COVID, it's kept a document called the master question list about COVID-19. And it always very, very organized way. They say, this is what we know, or we think we know, and this is what we want to know. So they had a master question list about COVID, things they didn't know. In the 26th of May, 2020, in that version of that paper, and which evolved throughout time. By the way, you can actually download it later in the presentation and check it out. And the versions change, but it still exists somewhere. All those versions, you can still find them. The Department of Homeland Security kept a very, very meticulous record, which is very good. I give them a good grade because this is one of the most important documents that you can extract information from. They did a very good job. But even with all this, in the 26th of May, they were still asking that question. What is the average infectious period during which individual can transmit the disease? Why is it important? Think about it. You are now the government, and you have to decide if you have a lockdown, or how much time do you keep people in curfew, or even if they're sick, how much time you keep them not roaming around? They didn't know. They kind of admitted. So since the Department of Homeland Security didn't know those things, and they asked us, and at this point, I started looking for answers. And actually, this happened later on in the pandemic, because some of those models came in like a year later, but some of them existed even before. So you can extract some information which is semi, like from this paper from Bai Li. And let me explain what this curve means. This is the infectious curve. It's relative infection. It tells you how much virus you shed, meaning how much virus your body gives away compared to your max. Your max is 1. So how much virus your body generates. And this is the day. So at day 0, almost nothing. You just got infected. You don't generate the virus, or at least not enough to actually spread around. The number is so low, you don't see it. And then for next 2 days, you don't. And then it starts growing, and then it goes away. This actually, in this case, in this paper, I actually took the information from I took this information and manipulated it a little bit, because it was not exactly like this. But some other models, they actually say, this is how we measured it. Notice how different the models are. Here's another one. Actually, in this paper, they had like 6 of those models, 5 or 6, I don't remember, but each one looked different. So I took 2 from that publication. And think about it. Each person also behaves differently. When I run the simulations, I run the simulation for each individual. So each individual may be different than another. But in this situation, I assume that all of them have the same infections, so the entire cohort, and we're looking at the average. We can do the simulations not like this, but we're looking for the average curve. So even if I say, oh, this is like that, or this is like that, or this person behaves like this, or like this, some of those papers came in later in the pandemic. But still, once you have this information, or even if you don't have this information, but you have assumptions from other diseases, say, oh, in this disease it looks like that, and maybe it takes the infection curve from that disease. You can plug it in. And what the model does, it uses AI techniques. Everyone probably is familiar with optimization technique called gradient descent. So using gradient descent after running all of those simulations, it will find the optimal one from all of the models that you plugged in. Let me explain how it starts. At the beginning, you don't know what curve is dominant or what is actually correct. What you do is you assume all models are the same, meaning if 5 people come to me and tell you a story, you believe them all the same way without knowing anything better. So you just average whatever they're saying. This is the average of all of the models that you saw before. Now, during simulation, you actually run simulations and know this is better, this is worse. And little by little, you start optimizing. And after many, many, many iterations, which take a lot of computing power, this is basically how AI models train, using very similar technique. So I'm using the same technique over some other medium, which is not a neural network as you know it. It's somewhat similar, but not exactly. It's a different state thing, state transition, and it actually runs a little bit differently. I can go into details if you're interested. And then you end up with something that looks like this. This is the answer for the Department of Homeland Security. Hopefully, in the future, you will see they will use technology and be able to extract an answer fairly quickly. And then don't go a long time in the pandemic without knowing. By the way, this may change with the numbers, but over time, and of course, there's virus variants and stuff like this, but at least the beginning, you have this basic idea of what's happening. And this is what was happening according to all the numbers and all the assumptions that you will see coming in later on. Remember, a model is not true, it's an assumption. And what it does, it takes all this ensemble and kind of puts it into places. This is the most reasonable set of assumptions that matches the best, the data best. Anyone has any question, or can I proceed? Okay, I'll proceed. Here's about transmission. I'll make it interesting for you. If I ask you if you met it's one thing being infectious, but what if I meet April 2020, I have COVID, and let's say I meet one of you for 15 minutes. What's the chance of you getting the COVID from me? Don't answer it. I'll tell you, I asked this question many times, many people. Many people tell me 70% for encounter for, say, 15 minutes. And then I tell them it's lower. They look at me and say 50%, and then tell them it's lower. Then they get to 10%, and I tell them it's still lower. And then they end up amazed that it's only between 1% and 2%. Because what drives COVID crazy is not the fact that the transmission happens immediately. It's like if the virus will be so infectious, then everyone will be infected in no time. What drives it is the fact that we have so many interactions amongst ourselves. So a person meeting, and we have those every day with many, many, many people. So if at some point me having interaction with one person, the chance is very low. But since I meet many people for many days, this is what drives it. The chance for me transmitting with 1% over 10 days with many people, it's much, much higher than me with one person for 15 minutes.
Doesn't it change depending on the length of the time you spend with the person?
Yeah, you can argue that. You can argue. Think about encounter. Think about like a 15-minute encounter as an average. If you spend the person twice, then basically it's not twice the probability, but it's very close to twice the probability.
What I'm saying is that let's say you meet 100 people for 1 minute, versus one person for 100 minutes.
Yeah, so all of those things scales kind of differently. It's you know like a Bernoulli test? It looks like a Bernoulli test that you run many, many times. You have a chance of like flipping a coin that is biased, and how many times each period of time, let's say 15 minutes, you flip one of those coins. So according to this, you can actually calculate an approximation to the function. So it's simple statistics that you learned at school, but now it's actually being active, very useful in those cases. Later on, we tried in the past to do it in the Markov model. There are multiple ways to calculate it, and some people come up with different functions. It doesn't matter really, because all of those are assumptions. All those models are incorrect to some degree. The question is which one is most plausible under all of the things that you know. And for this, you need a lot of assumptions, a lot of computing power. And this is what I solve. So even if it's not a Bernoulli test and someone else comes up with a different infections function, I can plug it in and see what happens. You understand what I mean? But in this situation, I took multiple functions that took into account the individual encounter, the population density of the state, some random constant, just plug it in just in case to make some noise. Sometimes it's helpful in some models, at least even to root out some things. And I also added something interesting, temperature. Here, let me ask you, what happens colder states or warmer states, the transmission is higher? Think about it. If you're in New York or Michigan, or you're in Texas or Florida, where is the chances for you to actually transmit the disease higher? Think about it. It matters. And we'll see the answer at the end. Think about the answer to yourselves, but later on you'll get the answer from me when I show the results. So I also took into account response models. Pandemics are also, it also matters how people behave. If you are afraid of the pandemic and you stick at home and don't go nowhere, your chances of transmitting or getting disease are much, much lower. But then, if you run around and ignore the disease like many people did, and which is model number 3 here, that say, oh, I don't care about COVID, and then eventually get COVID, and then you're at home and don't see anyone because you're at home. Or even worse, if you are not at home and you just ignore COVID and go around, it's worse. So different people behave differently. Actually, different parts of society behave differently. Same just like infectiousness curve. Each one behaves differently. So now you have different models. So I took 2 models from Apple Mobility with different variations on them. Apple Mobility data says, oh, how many people looked at their phones and pressed the map button? This indicates they want to go somewhere. It doesn't mean they went, but this kind of an estimate of how much mobility they had. So this is, I use those as a base. Also, I used as a base, later on came Eric Ferguson. I hope I didn't butcher the name. He's from Montclair University. He did a study of US states and knew whether what their shutdown orders were. In the states, each state decided differently. So now you incorporate all of this into the model and say whether non-essential shops were closed, schools, stay-at-home orders, and so on and so forth. And at different levels of compliance, I entered it as a formula into the model. It's a little bit more complex. I'm just giving you the idea of what's happening here. He later on published a good version. I used an older version and I state exactly what the differences are from this newest version. But this is how now I have different models on how the states behave. And each state behaves differently, of course. But I have also different models of those, and all of those are part of the mix of models that are playing around. Think about it. All of those models are roaming around and doing things. Then Kayode came in and tell me, this is fairly recent, he gave me an hospitalization model. I didn't have an hospitalization model, meaning people are in hospital. The numbers that you count of people being infected is not very good estimate because, the tests are not that. You don't test everyone. and so on and so forth. And there's errors here, errors. But people who ended up in the hospital, oh, you know, they were hospitalized. So if you have a hospitalization model, it kind of like helps you out. Now, interestingly enough, not all states counted hospitalizations well, but it doesn't matter. When they do, I do want better information. So hospitalization models is something that Kiyode gave me. And then the question is, when does the person, what's frequency the person gets hospitalized if they get the disease? So he came up with 3 models: low probability, moderate probability, and high probability. And those depend on age, as you can see here. And also whether a person gets hospitalized early or later, meaning how much time it takes them to get hospitalized and each age when. So again, you can run the simulation and find out that the worst summary, if you take the average one, it's not the best one. Actually, the one with the lower probability, the hospitalization was not as high as we thought, at least according to the data and all of the other models that we found. So all of this you take into account. Finally, we have mortality models. People die out of COVID. They die, they eventually everything. But then what frequency, again, what's chance of dying and when? So there's one type of modeling saying, we'll take, this is information published by the CDC, we'll take between some average, this is more complicated. I'll just say that it's the mortality probability and the time, and it doesn't change much. But Filippo Castiglione actually did a model about how organs die out of cells dying. This is a multi-model, like a multi-scale model, because he was working in level of cells, but later on tied it all the way up to the mortality of the person. So it's different levels of size. So this is why it's called a multi-scale model. And that model, it tells me in each day after infection is D0, what's the chance of a person dying? So for example, a 20 or someone, an infant dying out of day 19, 17, according to his model, is less than 1 per 1,000 if they get infected. But if you go to a 90-year-old, in day 20, it's 1%. In day 19, it's a little bit less. It's also 1%, but then it drops and goes high. This is according to his model. So now, which one of the models is correct? So you can mix them up and check it out. And this is what we do. But before we do this, we also have to account the fact that the numbers we get are incorrect. How many people here, raise of hands, how many people here saw something about the numbers that they are showing are wrong? Someone is miscounting them during COVID. We all went through COVID. Come on. Gabor, did you ever?
I definitely did, yeah. I can't raise my hand, but I could raise my voice.
Yeah, so we know that the numbers people claim they are wrong. Some people claim we're overestimated, some people claim they're underestimated, correct? Everyone had their own opinion, and we don't know what drives those opinions, but we can suspect, but it doesn't matter really. For science, we have different numbers and we don't trust them. How do we correct them? Say, you know what? We ask the question, what if it was a different number? And what different number? For example, we know almost for sure that the number of infections that we have is miscounted. It doesn't represent the probability in the entire society. Like probability of, not probability, the proportion of people actually infected in society, because the tests are always like they have an error. It also matters when you test the person. It matters not only when you test the person, it's like in the accuracy of the test, but also how you conduct the test, how you, like what your sample, what your sample population are, all of those things matter. So we pretty much assume that the numbers are underreported, the number of infections, people that are reported, because there are those who never tested, therefore their numbers didn't appear. So now, how much we multiply them? Well, some people multiply by 5. This seems to be like a running number that everyone multiplies in epidemiology. I claimed, okay, let's try 20. Just if there's 5, let's try 20. Lucas, who gave me this model, I actually gave you an infectious model, Lucas Botcher. he actually looked at, he says that it's also about 715. You have to multiply the infection with 715. And then there's another model that it's more complicated to explain. We'll leave it for now. It doesn't matter for now. And then the mortality is the same thing. Same people who died, people who died out of a car crash were listed as COVID. At least this is what was reported in some newspapers. And vice versa, some people who died out of COVID maybe were written down that they died out of something else because of complication. We never know. So you can actually do this, and this is what Lucas Watcher did. And he did it per state, and he gave me a bunch of numbers per state. So now I'm running all of those models to make sure that whatever is being told is correct. So now we have the two numbers, the true number that the model knows of how many people are infected, and the observed numbers, which takes all of those and adjusts this to according to the real number. So in the observed number, it will be different. So now let's look at the results. This takes a lot of computing time to actually do. It's about 3 years of computation on one CPU or on one CPU core. I use a 24-core machine, so it takes about 6 weeks to run that simulation that you see. I'm now running a much, much bigger simulation. I might show you on the screen while it's happening later on. Each state is represented by 10,000 individuals, and those 10,000 individuals interact kind of with each other and also with all of the equations that I showed you. And each equation comes in with a different weight. And what I do is I run all the simulations and then test whether the numbers match or don't, how well or how badly they match or don't match the reported numbers. So let's look at this. It's a huge, I cannot even show you the real results. This is a cut down version, because otherwise the file sizes become enormous at some point. But let's explain what you're seeing. This is the population panel. You see here for each state, multiple of those circles. Each circles represent one day in one simulation, and I restart simulations again at different times because remember, like you have the timeline running, and I start the simulations once in day 1 and then once in day 5, and then check it out after whether day 10 in one, which means day 5 in the other, are the same. I include all of those together because if I start all the simulation at the same time and some of the numbers are wrong, then I have a problem. So I have to start the simulation at different times in the pandemic and in different windows. Each time I run a window of 21 days. And then I check after 21 days how good it matches the results. I figured out that if I don't do those windows, then the results are not really good. So those windows really help stabilize the results because all the numbers become, it's much less sensitive to wrong number, to some errors that appear. So what happens here is one circle represents, for example, let's take this circle. This is Kentucky. Cohort 45 means that it starts 45 days after April 1st. This is where the simulation starts, and then it runs for 21 days. So after 21 days, you can look at the results here. It will give you the average age and stuff like this. But look at the numbers that says observed infected. You will see a number before the slash and the number after the slash. Same thing, observed death, before the slash and after the slash. The number before is what the model tells you. The number after is the actual number as reported by COVID tracking project after, of course, being optimized, after being normalized to 10,000 people per state. So this is out of 10,000 people. So you see the model is way off, like twice here. Now, the height of that circle is the error. It's called the fitness score that takes into account the differences between the infectious, the observed infection model and the observed results, and the death model and the observed results, and the hospitalization model and observed results. They're all bundled together. And then this is being optimized using gradient descent, which is an AI technique that people are familiar with. This is what the base for all our neural networks is. So now I'm taking all of this and I'm starting to optimize. Notice the height of the circle is the error, and I'm trying to drop it down. Ideally, I want everything to be around 0. And what I'm actually optimizing, let's explain what happens here. You see all those 5 blue ones? Those are all infectious models. Those purple ones are transmission models. The green ones are the behavioral models. The reddish or brownish ones and the yellow ones are the hospitalization models. You remember we have time and probability. And those are mortality models. And finally, the purple ones are mortality observer models. All of those are being a hospital, optimized at the same time. So now I'm looking, I'm tweaking them, and I'm running gradient descent on their variations. And then little by little, you say, even like after 3 iterations, see one of the transmission models totally disappears. We'll tell you which one in a second. And then it continues, and see some here, more dominant mortality models. So some of the mortality models were not that good. And continue. Now you can build those curves I showed you at the beginning. You can actually figure out what the transmission was, how people behaved. You'll see the Apple mobility data disappeared completely. Within the transmission models, the model that disappeared and this one became dominant. Those are the ones with temperature. The ones with that says that colder states transmit more is the one that is dominant. Meaning, if you're in a hot state, you're better off than in a cold state, because this almost disappeared completely. Here in the infectious is one, you see that some of the dominant models, the one that were longer, not the one that shorter. And finally, if you look up the mortality model, the one that Felipe Castiglione gave me is the dominant one. Meaning these models actually better if you look at it over time. And observer models tell you that some of the models don't make sense, like don't multiply by 20. It's somewhere between 1.5 or 7.5 or 7.15. Approximately, the people who says that 5 times, if you multiply the number of infections, the correct number, those were generally correct. Approximately, we can actually calculate the exact numbers, but this doesn't matter because it's enough to know that it's what's wrong and what's not. And now we can answer questions about the pandemic. And I've written all those things here, but let's talk about a little bit about conclusions. I'll just conclude everything in case you might have questions. And I want to go too much over time. I want to keep it short, otherwise it's me talking. I want to hear you. So the idea is that this model can help the government in the next pandemic. Now, I'm telling you this, but I am biased because I developed it. This is developing for about, since 2012, I invested all my time and effort and resources into this, quite a bit. I've been doing this for many years on my own. I'm a sole proprietor now, meaning I'm a company of one person in the US. It's a form of explainable artificial intelligence because I can explain to you things as you saw. So it's AI, but the explainable type, ones I'm showing you. It's sometimes, now the question is how good it is. So I can tell you for sure, it is difficult to explain phenomena like COVID-19 because there are many, many parameters. And the question is how much time you know, because in the next pandemic, if someone comes to me and asks me how good this tool will be, I tell them, well, you have to have at least 3 weeks of data after you're having some sort of infection going on. I started modeling April 2020. So you need at least 3 weeks of data, but this is actually not true because 3 weeks of data will give you, initially when I did this, it will give you different results because you don't have enough numbers. You have to follow it for at least several months and then do the windows I'm talking about, and then the numbers started stabilizing it. I'm still running a big simulation here to make sure those numbers are correct because I'm doing Monte Carlo simulations when I flip all those coins, and I'm making sure that I throw enough computing power at it to actually make it useful, and that I didn't make any mistakes. Eventually, every once in a while, I find something that it was wrong that I need to correct. This is why there are multiple versions. But in the future, you'll need at least a few months of data. Plus, you have to run with those windows, but maybe you'll get initial results after a month or two, and at least some sense you'll get. And then later on, you'll go with it. So the government will not be completely clueless like it was in the pandemic, because now we find out how clueless they were. Now, I can tell you that the peak average infections were about day 5 from infection. This is for COVID. And transmission rate is about 2% per encounter. It's a little bit less. But warm weather seems to reduce transmission. Now, this is something important today. We published the paper, Lessons Learned from COVID-19, from modeling COVID-19, and steps to take in the next pandemic. Here, I'll show you the paper. It will load. It's now in the preprint. We have multiple collaborators, and they have actually came from different perspectives. I did the reference model, but they did other models that figured out how to do other things better. And we wrote down the paper. It says how to do modeling better, how to spread information better and get it correctly, how to validate the information properly, and also we have some recommendation about infrastructure and education that will help. So if you're interested, please go and read the paper. It's in preprint. You can get it by following this link, number 53 here. All of what I showed you here can be reproduced to some degree. I'm showing exactly what data I did, so I can trace back if someone ever asks me about the presentation where I got the numbers from. The code that actually created the presentation, you can find it on GitHub. I actually released it, but not all of the data. Some things are proprietary. I have a conflict of interest statement here because I do intend to get money out of it. I have 2 patents, US patents on this technology. I'm now licensing them. If someone interested, knows someone who's interested, please do connect us. And I have many people to think, and many organizations. Some people gave me some all sorts of help. People from Holoviz allowed all this presentation technology I did. Midas helped me out finding some resources and connecting to some people that helped. People hosted my computer, published the video. You can actually see this. This is the video that's embedded. You can actually look at it later. So it was published in SciPod. People who contributed models. I'm showing some of the other work they did here. People who contributed money to actually run simulations on cloud. I actually ran several simulations on the cloud, which instead of several weeks or months, they ran in 2 days. But not all the time you have money for that. So Rescale gave me money for Azure and Amazon, and Midas gave me some money. I ran simulation on the Google Cloud with them. They gave it through some grant. And many people I have to thank throughout the way for various ideas or things. So thank you all. And I'm open for questions. I'm gonna leave this.
So Jacob, have you been able to use any of it on like bird flu or any other pandemics that are starting or rumored to be the next pandemic?
Currently, I'm focusing on COVID because this is technology that's still, believe it or not, it's still in development phase. Because here, you show me any technology that you invested 20 many years in. Is it something good enough? 20 many years? This is what it's about 20, it's about 20 years of development. You tell me. So I'm still making sure I'm cutting all the bits and pieces. So for this, such technologies, you need many more resources to actually, meaning I'm not talking about, some game that blows up that people use or something that is fairly tested. Sometimes they are not really tested, they just blow up like virally. Here, you actually, to be correct that this technology works, you actually have to invest a lot of time. Now, the big problem with all of the data, which is a different project that I'm making, is the fact that you cannot get medical data. One of the advantages of this project is that it can actually merge data from multiple sources. This is practically not allowed in the medical world, because if you have population A and population B, in the medical world, they are not allowed to merge the data between those two. No, because it's patient data, so the individual data is not allowed. But you're allowed to merge the models, and this is what I'm doing. This is why this technology is important, not only for the pandemics I'm doing. I'm doing it on the pandemics because there I have good data. The other model I have is the diabetes model. Today, as far as I know, I have the most validated diabetes model worldwide because I tested it with more population than anyone else. How did I do it? I connected to clinicaltrials.gov, got the information from there. But the thing is, even data in clinicaltrials.gov is not that good. Here, I'll show you. That's another project that I'm working on. Even to get the data out of those models, it's impossible because the units of measure are messed up. Even if you do it correctly, I'm going to show you just only one thing. It will take a minute to load. This is a website that's actually active. You can check it out. But like here, HbA1c is a measure of diabetes. So see how many ways people write HbA1c, the units of measure. A computer cannot understand it. So you need AI to tell it how it's supposed to be. And that's a different project I'm doing, which is a spin-off of this project. And actually, there's some claims in the patents that relate to this project as well. So eventually, being able to get the disease models correctly, you need correct data. You messing around with the data is the biggest problem. So you're saying bird flu because everyone says bird flu, but you have good data about bird flu. Well, once you start with COVID, you didn't have good data. And this is why we had this project running. And this is where recommendations how to get good data for the future and how to do it so we can models can use it, can actually get the results I got. It took me about 5 years to get to the something stable that I'm showing you now. And I started at the beginning of the pandemic. In the next pandemic, if it'll be 1 year, it will be better. And then it will be 3 months or 2 months or 2 weeks. Then it will be better and better and better. But to get to that point, we need an entire lubricated system that gives us all the things that we need, all the correct data and all the correct models and so on and so forth. This is still a lot of work. The big systems are not yet set to it. And hopefully this paper will be helpful in this regard. And think about how much money was thrown in COVID and how many models are out there. Think about some big machine that crunches all of those assumptions in the future that people plug in and tells them, oh, this summary is probably incorrect because it doesn't match this data or that data. This is what my technology does. And we do have the computing power today, but we do need the software infrastructure and all those many years that I only started. Did I answer your question, Jim?
Yeah, and very well. So it is again, Jacob, if I restate, right? So it may not be directly translatable to bird flu, but the lessons learned in the prep work, right, will get us to those answers faster using this example and this work.
I didn't try it with bird flu. If you give me data of bird flu, I can try it, but then I'll tell you, oh, this is missing and this is missing, and I need all those assumptions. And then you'll start finding all those researchers, and they won't go even. Finding researchers even to collaborate to give you all those models also takes time. All of this has to be centralized in a way that the system was during COVID, everything was kind of a mess. I wasn't part of that mess. I was trying to find things. I couldn't find them. And I believe I was stressed because I was working on this for, at that point, like 15 years, and I still was feeling that I don't have everything I need, like all the pieces and pieces. Now we're trying to normalize it and give more recommendations how to do it better in the future. The idea is that someone who actually is interested will look at it, learn from it, and then start training groups that will do those things. I have a friend who actually has some good ideas about this. His name is John Rice, and he actually was the instigator of this paper, saying, you know what did you learn from all this work that you did about COVID? So we organized it all in a way that in the next pandemic, there won't be such a problem. And we're now propagating this paper. If you're interested in helping, take this paper, send some of your friends.
Here, there's another question I see in the chat.
Shall
I read it out?
Yeah, please.
For type 1 diabetes modeling, isn't that a generic disease, autoimmune?
Well, type 1 diabetes is different than type 2. They have different mechanisms. I'm not a medical doctor to go into those. It was explained to me many times while I was doing diabetes, type 2 diabetes. I was working with a team of experts, worldwide experts in diabetes. I'm less concerned about the type of disease or what it is. Diseases for me are state transition models where you jump from one state to another and there's a probability of moving there, and the probability depends on all sorts of parameters. So the source of the disease or the cures, I don't care much. I just want to be able to explain it. Explain it, and how do I explain it? If I have a model that says A and then model says B, I want to know which one of those contributes more to the numbers I see at the end. The way I look at the diseases, it's all numbers. And some people who understand all of the elements, they are the ones making the models. So does it answer your question? Okay, so this is why it is, and I'll try to send you the link for that. Here we go. This is the link for that paper, the lessons learned paper. So if you know people who are interested, please propagate that. This is important. Hopefully some governments or some organizations will adapt, and next pandemic will have less mess than we had in this pandemic. By the way, when I started the pandemic, everyone was doing COVID. Really, like every department, every institution was like, financial institutions were running COVID models. Computation institutions were having COVID. Everyone had COVID model. Now I even talking to people who model COVID is kind of hard because they all stopped doing it. It's less interesting. But for me, it's interesting very much to know, because I'm really am dedicated to it, and this is my life's work. I've been working on this almost 20 years, and I want this to continue and done properly. So this is why I'm giving this talk. And Gabor, thank you for having me.
Thank you for giving this talk, this presentation. And anyone, any more questions before we close the video?
If you have Python questions on how I did this with Python or how I did that, it's also I'm running many things. Actually, maybe it's a good time to show you. You see this thing, hopefully I won't disconnect everything. This is a screen of a computer. Behind it is a 24-core machine, like a very good processor. It runs as fast as the older supercomputers, 32 core, 32 threads. And this simulation now, it's in 17.
If you stop the screen sharing, you'll see better.
Okay, I'll stop the screen share. Second. How do I stop the screen share? I think it shows me screen share. How do I stop it? It says only share. Did I stop the share? No.
No, not yet.
Give me a second. I'm not sure how to stop the share in this model. I
did it.
Okay, thank you. You see this? This screen is actually a computer that runs simulation. Same simulation you're seeing now, it's run here. This is iteration 17. It should get to 40 to get something stable, approximately. This is my currently baseline. I'm seeing all the simulation 40, but this one is like much bigger. Here, I start the simulation in each day, and I run 5 repetitions for all of this. I'm actually running about like 2 months of day for, I have information from April to June. And each time I start a different day and run for 21 days and check the numbers for 5 simulations for each state. And then I continue doing this. And this will take me about half a year. I started a few months ago. And I had some interruptions, power problems, and so on and so forth, computer problems. I actually burned computers on this. I kid you not. I have multiple computers dead because of running all those simulations, running all throughout the world for many, many years. So I started with small clusters. I created clusters. I use Dask to create clusters. To this, it still runs with Dask. You can see the Dask.
Yeah, we can't really see that now. Well,
Apologies, I cannot make it much fast closer.
but it's very bright.
I apologize. This is the best I can do.
Yeah.
Anyway,
Okay. Well, thank you very much again, and thank you everyone for being here. And if you're watching, I mean, you shared links so people can find you. They will be under the video. There will be a link for all these things. Like the video, share, follow the channel, share the video, and talk to Jacob if you're interested in discussing this topic.
Please.
Thank you very much.
Thank you.
Bye-bye.
Bye-bye.